Now, what is that situation? So let's say this is the ground, this position is the ground position. An object was taken to a certain height and then released from there. So it could be a building, could be anything. Then a person goes to a specific height, then releases an object from there. Could be a ball, could be anything. The object is released from that height. What do the graphs look like? We'll be discussing displacement time graph, we'll be discussing the velocity time graph, and then we'll be discussing the acceleration time graph. So let us start off with the displacement time graph first. So this is the first one that we have. I'm going to label x-axis with time, and I'm going to label y-axis with displacement. Displacement represented by the symbol s. So what does the shape of the graph look like? If there is no air resistance, as the object is released, initially when the object was not released, the speed was 0. And if this is our reference point, the point of release, let's call this the reference point, the displacement is also 0. If this is the reference point, the displacement is 0 and the velocity is also 0. But as it goes away from the reference point, the displacement would increase. One of the convention is that when we use the equations for free fall, the 4 equations, when we use them, in those equations we use a convention that when an object is below the reference point, displacement is negative. When the direction is downwards, the velocity is negative. That is a specific convention for the equations of motion. We can totally use the same convention here also. But what if we go with the other way? So I can say if I go below, if I go downward, my displacement would be negative. And if the object is moving downward, the velocity would be positive. We can have this convention because we have a single situation, the object is going downward. We can make a convention so everything is positive for us. This is one of the way. So what do the graphs look like according to this convention? A velocity positive downward and displacement below the reference downward. Well, the displacement time graph will look something like this. Which, if you could remember, is the graph for the accelerating body. And the body does accelerate, the object does accelerate, it speeds up due to the influence of the gravity. It does accelerate, so the object is accelerating. And in the free fall motion, an object has uniform acceleration that we know as the acceleration of free fall, and the value of it is 9.81. This is the convention that we have made. We can totally have the reverse convention, and I would be explaining why do we have acceleration as positive. So I'll put a star over here. I'll explain according to this convention Why the acceleration positive? I'll explain in a moment. Now let's move on to the velocity time graph first. For the velocity time graph, let me draw the axis. So here we have the axis, time on the x-axis, and velocity on the y-axis. According to our convention, and you can totally change the convention, you can change it every time, but for the equations of motion, you use the same one. For the four equations of motion, you use the same one that I explained already previously. Now, the convention was if the object is moving downwards, the velocity would be positive. Yes, it is moving downward. And initially, you see the initial velocity was 0. As you release it, it speeds up. It speeds up even more. The speed increases more and more. But the acceleration is uniform, which is acceleration of free fall. So what does the shape look like? And in that case, the velocity time graph would look something like this. What does that mean? The gradient is positive. Okay, we'll talk about the gradient afterwards. You see the velocity was initially 0, then it increases, 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 increases. And as the object falls down, the velocity increases. So this is what the velocity time graph will look like for the object thrown downward with this sign convention. Now let's take a look at the last thing, and that is about the acceleration time graph. So if I could draw the axis here. All right, so this is a situation that we have time on x-axis, but this time I'm representing acceleration on y-axis. Now the question is, if we have the velocity time graph, how do we find the acceleration from velocity time graph? Or what thing of the velocity time graph gives us the acceleration? Would you answer that? Gradient, exactly. So could you answer me these two things? The sign of the gradient and the value of the gradient. Means is it fixed, is it uniform or non-uniform? So first of all, give me the sign of the gradient, positive or negative? Positive, very good. The line is rising, gradient is positive. What about the value? Constant or non-uniform? Constant, exactly. For a straight line, the gradient is constant. So if the gradient is constant, if the gradient is positive, and you also know that the gradient of velocity time graph, the gradient of velocity time graph gives acceleration. So can we say the acceleration would be constant and positive? So the graph for the acceleration would look something like this. So you see acceleration throughout the motion remains constant, and it should be exactly how much? 9.81. It should be constant with a value of 9.81. It remains constant, and also because there's no air resistance, it remains constant. It does not decrease. If we have the air resistance, it then decreases and eventually reduces to 0. The velocity at that state is known as terminal velocity, but that's the discussion for the next chapters for the forces. So this is what the acceleration time graph would look like. under this, once again, under this, what do you call that? Convention, sign convention. If you reverse the sign convention, the shape would remain same, but the direction of lines would be reversed. So let's move on to the next one, which is a situation when the object is thrown upwards. So situation 2, object thrown upwards. So for this one, I'm going to assume, consider the motion into two parts. The first part would be, let's say this is the ground. In the first part, the object goes upward. It reaches to this point. This is the first part of the motion. And then in the second part, the object comes down to the starting point, to the same point. So this motion would be in two parts. The first part is this one, as it goes up, and the second part is this one, as it comes back to the ground. So let us consider the first part, when the object is thrown upward. When the object is going upwards. And we'll have to consider a sign convention also. So upward motion, the velocity upward has to be taken as positive or negative. So what convention do we use? So the easier thing would be, I'll say whatever the initial motion was, the direction of initial motion was, consider it positive. So initial direction of motion, consider positive for velocity. Initial direction of motion is considered positive for velocity. And likewise, the initial direction of or initial position of the object can be taken as positive for displacement. So can I say object above the reference would be positive displacement? Object above reference has positive displacement. This is what the convention is. Why do I have this convention? I have taken this depending on the initial conditions. Initially, in the first part, the ball is thrown upward. So I say upward velocity is positive. When it comes downward, then the velocity would be negative. And since the object remains above the reference point, I use the convention, if it is above the reference point, then displacement is positive. Let us draw the graphs now. First of all, I'll be starting off with displacement time graph. Alright, so the first one is the displacement time graph. Let me draw the axis for that. Or I can draw all three of them. One for displacement time, one for velocity time, and the last one for acceleration time. So the first case is when the object is thrown upward. So I'll raise off everything else. Just consider this part only. When the object is thrown upwards. So the object goes from here and goes to the maximum point, and you see at the maximum point or at the maximum height, the velocity would be 0, and then it will fall downwards once again. So this is the situation that we have. And my convention is same. This one, above the reference, displacement positive, and direction of motion upwards, it has positive velocity. So if this one is displacement time graph, what does that look like? So initially, as I move away from the reference point, my displacement increases, and it increases with a positive value. Why is it positive? Because that's my convention. So the displacement increases initially like this in the first half of the motion when the ball is thrown upward. And as the ball reaches the maximum height, it has the maximum displacement. When it falls downward towards the reference point, the displacement then decreases, and when it reaches the starting point, back to the reference point, back to the ground, the displacement would then be reduced to 0. So we have, for the first graph, which is the displacement time, you can see we have two parts of it. I can even draw a line, a very faint line. So the displacement time graph has two parts. When the ball rises up to the maximum point, this part represents that situation, and when the ball falls downward, the second part represents this situation. And you need to ensure that the distance on this side and on the right side should be same, because the reason is it would take, the ball has to take, or the object has to take same time to go up and to come down. So if this is 2 seconds here, then that should also be 2 seconds. So in simple words, there has to be a line of symmetry for the shape. Let's talk about the second graph, which is the velocity time. So time on x-axis, and we have the velocity on y-axis. Let's talk about the velocity time. The first part, let's consider the first part only. When the ball is going upwards, initially it must be launched with a specific velocity, with a very high velocity, and then the velocity decreases, and eventually at the maximum height it reduces to 0. And since there is no air resistance, the acceleration should be constant, which should be equal to the acceleration of free fall. But initially, what you're saying is, initially the velocity should be maximum, and then at the maximum height it should be reduced to 0. So what does the graph look like? Well, we can join these 2 points like this one. So this is the part when the object goes up. And what is this point representing? This point represents maximum height point, the point of the maximum height. What happens afterwards in the second stage? When the ball is to the maximum height, now it falls downward, and this time there are 2 changes. When the ball falls downward, there would be 2 changes. One of the change would be, this time the velocity should increase. As it falls downward, now the velocity should increase. And the second change is, now velocity should be with the negative sign, because the convention set initially was, if it goes upward, you take it as positive. If it goes downward, you take it as negative. So our velocity is negative, and it is increasing. So the shape of the graph will look something like this. I would increase to the same interval of time till the same interval of time. So this time over here should be equal to this one, and the velocity, the maximum velocity at the start, should be equal to the final velocity at the end. So in other words, this line, this length should equal this length, and the two times should also be equal. What is the second part representing? This is the part when the object was falling downwards. Two changes are there. The direction of the velocity is reversed. Velocity is a vector quantity, so you need to reverse the sign. And the velocity is now increasing. So you have to increase the velocity graphically also. So in terms of numbers, what does that look like? So you threw the object upwards. Let's say the velocity was 20. Initially the velocity was 20. As it goes up, the velocity decreases, let's say 15, then 10, then 5. To the maximum height, the velocity was reduced to 0. And now it falls down. The velocity increases, but in the opposite direction. So it could look something like this: -5, -10, -15, and -20. So this thing and this thing is equal, but with the opposite sign. This is what this situation would look like. Now the next thing is, how do we draw, or how do we find the acceleration through the velocity time graph? How do we find the acceleration? Again, the answer is same. We can find the acceleration by finding the gradient of velocity time graph. So could we find the gradient of this straight line? You see, we have a single straight line. It is just a single straight line, although they are representing two stages. But in terms of the shape, we have a single straight line. Now let me ask the two questions. Is the gradient positive or negative? And is the gradient uniform or non-uniform? So first, if you could answer me about positive or negative gradient. Which one is that? Negative, very good. The gradient is negative. And uniform or non-uniform? Uniform, very good. So what does that mean? Well, it means that the acceleration would also be negative but uniform. So I have to stretch the y-axis downward also, because my acceleration is negative, but it is nevertheless uniform. So the shape of the acceleration time graph would be something like this. And what is this value, to be precise? Well, that is minus 9.81 meter per second square. So you see, the object going up or down, we have considered the convention. Our acceleration is minus 9.81. And this is the usual convention, the traditional convention, or the most famous one. When the object is thrown up, you consider the velocity as positive. When it falls down, you consider it as negative. But you see, the shape of the graph is this one, which is the line falling down. The line is upside down. The gradient has to be negative, hence the acceleration has to be negative.